In the 1950s, United States railroads ruled the speed game. Their diesel giants topped out near 190 kilometers per hour, until a French electric prototype thundered past 331 kilometers per hour, smashing every American record in a single afternoon. What made America so sure they could never be beaten? And how did one machine from France change world rail forever? The answer begins where the American advantage quietly ended. American railroads in the years after World War II moved millions of people and vast quantities of freight across a continent. But their passenger trains all ran up against the same hard ceiling. The numbers were clear in every timetable and test report. Top speeds for daily service rarely exceeded 160 kilometers per hour, or about 100 miles per hour. That figure was not just a suggestion, it was the practical limit for nearly every express in the country. Even the most ambitious runs, like the New York Central's 20th Century Limited or the Santa Fe Super Chief, were scheduled around this cap, with only brief sprints above it, if at all. The technology behind these trains was the pride of American industry. The Electromotive Division, EMD, of General Motors produced the famous F and E series diesel electrics, while Alco, the American Locomotive Company, fielded its own PA and PB models. Both lines dominated the rails, pulling the nation's flagship passenger trains from coast to coast. On paper, their engines could deliver up to 2,000 or 3,000 horsepower. In reality, their gearing and weight limited them to consistent speeds well below what their marketing promised. Test runs occasionally pushed the boundaries. Factory demonstrations and controlled trials sometimes nudged close to 190 kilometers per hour, about 118 miles per hour. But these were not everyday achievements. The infrastructure simply was not built for more. Track geometry, signaling systems, and even the quality of the rails themselves forced operators to keep speeds in check. Insurance companies and government regulators, wary of the risks, reinforced these boundaries. The Interstate Commerce Commission, which oversaw rail safety, rarely authorized anything faster for regular service. The result was a plateau. By the early 1950s, American passenger trains were locked into a narrow speed band. Expresses like the Pennsylvania Railroad's Broadway Limited and the Milwaukee Road's Hiawatha routinely ran from 130 to 160 kilometers per hour. Anything faster was a publicity stunt, not a sustainable practice. Diesel technology, for all its reliability and power, could not overcome the drag of physics and the constraints of the existing rail network. This ceiling was not just a technical detail. It shaped the entire approach to passenger rail in the United States. Dieselization brought efficiency and lower operating costs, but it also set a limit on what was possible. The industry focused on comfort, style, and frequency, rather than chasing ever higher speeds. As a result, the numbers in the record books barely budged for years. The American rail system, so often celebrated for its scale and might, quietly accepted a maximum that seemed, for a time, unbreakable. American railroads were run by private companies, each with its own bottom line and its own vision for the future. This structure shaped every decision, from the types of locomotives they bought to the way they marketed their services. The major lines, names like Pennsylvania Railroad, New York Central, and Santa Fe, were locked in constant competition, but they shared a common approach: invest where the returns were certain and avoid the risks of unproven technology. For these companies, dieselization was not just a technical upgrade, it was a financial strategy. Diesel engines promised lower maintenance costs, longer intervals between overhauls, and easier standardization across vast freight and passenger networks. The numbers made sense to shareholders, and the trade press echoed this optimism. Railway Age, the industry's main voice, published glowing reports on diesel reliability and the steady march of progress. The narrative was simple. American railroads had found the formula for efficiency and profitability. This confidence extended beyond the boardroom. Newspapers ran stories about the modern marvels crossing the continent, and company spokespeople talked up the comfort and convenience of new streamliners. Speed was part of the sales pitch, but only within the boundaries set by safety and cost. The idea of pushing for higher and higher velocities seemed unnecessary, even reckless. After all, the trains already outpaced automobiles on the open road and offered a level of luxury that airlines, still in their infancy, could not match. Every new timetable and equipment order reinforced the prevailing wisdom: invest in what works, and avoid the financial gamble of radical change. Electrification, with its massive upfront costs and uncertain returns, was largely dismissed outside a few dense corridors. The American model favored incremental improvement over bold experimentation. If the system delivered steady profits and satisfied customers, why risk it all chasing records that had little impact on the bottom line? This mindset shaped public perception as well. Trade magazines and company advertisements painted a picture of American rail as the envy of the world, a symbol of industrial might and managerial savvy. The belief was widespread that the best trains were already running on American rails, and that any foreign effort to go faster was at best a curiosity, and at worst a distraction from the real business of moving people and goods efficiently. As a result, the possibility of being outpaced by another country was rarely considered. The industry's faith in its own model ran deep, and few saw any reason to question it. Southwestern France, spring of 1954. The landscape between Bordeaux and Dax, usually quiet and green, became the setting for a different kind of ambition. French railway engineers, determined to push beyond the limits of post-war travel, selected a 46-kilometer stretch of straight track through the Landes region for their experiments. The corridor, flanked by pine forests and distant villages, offered the uninterrupted distance needed for sustained high-speed trials, something rare in the winding, hilly terrain of much of France. Before any records could be challenged, the groundwork had to be laid, literally. Maintenance crews reinforced every section of rail, tightening bolts, adjusting ballast, and checking for the slightest imperfection. Maintenance teams worked methodically, checking every splice and weld. The overhead catenary, responsible for delivering 1.5 kilovolts of direct current to the locomotive, was inspected and upgraded to handle the intense electrical draw that would come with higher speeds. Upgrades focused on reliability and steady power delivery. Safety was paramount. Fences were erected to keep livestock and debris away from the right-of-way, and signals were recalibrated for the rare possibility of a train moving faster than any timetable anticipated. Every kilometer post, every curve, and every joint in the rails was scrutinized for weaknesses that might go unnoticed at ordinary speeds, but could become catastrophic at 200 kilometers per hour or beyond. Crews scrutinized geometry and fastening systems with extreme care. The SNCF had already tasted success. In February 1954, the CC7121, sister to the soon-to-be-famous CC7107, hauled a 3-car train at a verified 243 kilometers per hour along a similar test route. That achievement, while impressive, was seen as a stepping stone rather than a finish line. The 243 kilometers per hour run proved the basic concept that with careful preparation and the right equipment, electric traction could shatter the limits of conventional passenger service. But the French team believed there was much more to unlock. Each trial brought lessons. The rails themselves revealed their secrets under strain, showing where welds needed reinforcing and where the geometry had to be near perfect to avoid dangerous oscillations at speed. The catenary wires, stretched tighter than ever, were monitored for arcing and heat buildup. Even the substation teams, stationed miles apart, rehearsed their roles in delivering steady power as the experimental train flashed past at speeds that would have seemed like fantasy just a few years before. Behind the scenes, planners and engineers debated every variable. Should the train carry extra weight for stability or strip down for maximum acceleration? How much streamlining could be added without compromising safety or maintenance? The answers shaped not just the test runs, but the future of French rail engineering. Every adjustment was a calculated risk. Every improvement a step toward the ultimate goal. By the time the CC7107 was readied for its own attempt, the groundwork was more than just physical. It was a blueprint for how to challenge the possible. The track, the train, and the teams were all primed for a leap that would soon echo far beyond the lands. The stage was set for a new way of thinking about speed, safety, and what railways could achieve. The CC7107's record run was not a fluke. Every detail of the locomotive and its train was the result of relentless engineering, tested against the limits of physics and materials. At its heart, the CC7107 was a machine built to turn raw electrical power into forward motion with a precision that American diesels could not match. On March 29, 1955, the locomotive drew a staggering 8,200 kilowatts, about 12,000 horsepower, from the overhead catenary, a figure that dwarfed anything running on American rails. This current surged through 6 traction motors, each axle gripping the rails with just enough force to avoid slipping, even as the train's speed climbed past 300 kilometers per hour. Aerodynamics played a decisive role. The 3-car train was fitted with streamlining modifications, fairings, and smooth edges designed to slice through the air. Engineers knew that at these speeds, air resistance did not just slow the train, it became a wall. Every curve and contour was scrutinized, not for style but for survival. The locomotive itself, while not radically altered, was paired with cars that minimized drag, allowing the train to accelerate with a smoothness that belied the forces at work. As the CC7107 hurtled down the Landes line, the speedometer needle swept past the previous year's record of 243 kilometers per hour, then surged toward the unthinkable. At 331 kilometers per hour, 205.6 miles per hour, the train became the fastest locomotive in the world. The sensation inside the cab was one of controlled violence. The rails blurred beneath, catenary posts flicked past at nearly 1 per second, and the overhead wires thrummed with energy. Instrumentation showed the pantograph, the device that drew power from the wire, was reaching its thermal limit. The contact strip began to soften and deform, a silent warning that the boundaries of engineering were being tested in real time. The pantograph's performance was critical. At such speeds, it had to maintain flawless contact with the overhead wire, transmitting thousands of amps without sparking or losing grip. The heat generated was intense, enough to partially melt the contact head by the end of the run. Engineers later measured the damage, finding traces of arcing and material loss, but the rails themselves and the locomotive's running gear held firm. The stresses on the wheels, bogies, and frame were immense, yet the design absorbed them without catastrophic failure. The only true casualty was the pantograph, a price the team had anticipated. This was not a stunt that left the track battered or the train crippled. The CC7107 finished its run under its own power, a testament to the careful balance of force, adhesion, and electrical supply. The record was not the product of a single breakthrough, but of a system tuned to perfection, with power delivery, aerodynamic drag, and component durability all working together at the edge of possibility. For the engineers and test crew, the achievement was proof that their methods and their machines could do what no one else had managed. The numbers, 8,200 kilowatts, 331 kilometers per hour, and pantograph temperatures nearing destruction, were not just data points. They were the evidence of a new standard that would echo across the world's railways for decades. Electrification was the dividing line between what France achieved and what America refused to attempt. In the United States, the cost of stringing high-voltage wires across thousands of miles of track was considered prohibitive. Railroads calculated that electrifying even a single main line would require not just new locomotives, but an overhaul of signaling, substations, and maintenance equipment. The price tag for such a transformation ran into the hundreds of millions of dollars, far beyond what private companies were willing to risk for a market already under pressure from cars and airlines. Federal priorities only deepened the divide. In 1956, Congress passed the Interstate Highway Act, promising $25 billion for a new national road network. This single law did more to shape American transportation than any rail investment ever could. Highways became the backbone of mobility, drawing both passengers and freight away from the rails. Government funding for rail infrastructure, by contrast, dwindled to a trickle. Any talk of matching European electrification was dismissed as impractical, even romantic. Corporate leaders saw no incentive to gamble on unproven technology. Dieselization had already delivered clear savings in fuel and labor, and the returns were easy to measure. Shareholders demanded stability, not risky experiments. Electrification, with its massive upfront costs and uncertain payback, was a non-starter for most American executives. Even in the dense corridors of the Northeast, where wires might have made sense, investment stalled. The Pennsylvania Railroad's partial electrification remained an outlier, not a model for the rest of the country. The result was a self-reinforcing cycle. Without public support or private appetite for change, the American rail network settled into a pattern of incremental upgrades rather than radical improvement. The infrastructure that could have supported higher speeds never materialized, and the technical gap with Europe widened year by year. The numbers from the record run did not just make headlines, they became the foundation for a new era in French rail. Engineers and planners pored over every data point collected from the CC 7107 and its companion, the BB 9004, which matched the record on a separate run. The lessons learned went far beyond the thrill of a single achievement. They revealed how power delivery, wheel adhesion, and aerodynamics could be balanced for sustained high-speed travel, not just brief bursts on straight track. Within a decade, these insights shaped the launch of the Mistral, a premier express linking Paris and the French Riviera. By 1967, the Mistral routinely ran at 200 kilometers per hour in regular service. This everyday reality had once seemed out of reach. The same principles, tested to the breaking point in the Landes, guided the design of new locomotives and rolling stock. Electrical systems were refined for reliability at high speeds. And the experience with pantograph failures led to new standards for current collection and overhead line construction. The record itself stood as a benchmark for more than half a century. No other locomotive would officially surpass 331 kilometers per hour until 2006, when a Siemens Taurus briefly claimed the title. In the meantime, French engineers kept building on what they had learned, feeding data and expertise directly into the TGV project. The lineage is unmistakable, from the CC 7107's run in 1955 to the world's first high-speed rail network. The same spirit of experimentation and technical mastery carried forward. Every milestone, each new service, each new record, traced its roots back to the day when French railways proved just how far electric traction could go. Today, France leads in high-speed rail, while America debates its future on outdated tracks. The CC 7107's record reminds us, bold innovation, not legacy pride, drives real progress. As nations grapple with climate and mobility, the next leap belongs to those who dare to rethink what is possible. Sometimes, the race isn't won by the fastest, just by the first to imagine more. Share your thoughts below.